Welcome everybody to the third and final installment of the action-packed JavaScript trilogy. We're going to continue in our discussion of JavaScript. We're going to be looking at these topics today: inheritance, modules, debugging, efficiency, and then a little bit about JSON at the end. Okay, so as you recall, inheritance is object-oriented code reuse. It's a useful pattern of letting us make use of code, taking it further, reducing the cost of development. There are basically two schools of thought on inheritance. There's the classical school, which is what basically everybody was trained in, and then there's the prototypal school, of which JavaScript is about the only instance. As you recall, in the classical school, objects are instances of classes, and a class inherits from another class. But in the prototypal school, it's class-free. There are no classes. Objects inherit directly from other objects. The way JavaScript accomplishes this is that every object has a secret link to another object from which it inherits properties. Mozilla gives this secret link a name. They call it Proto. Proto did not get into the language specification and isn't in the other implementation, so I recommend that you not use it because it's not portable. But if you ever do see it and you wonder what is this proto jazz in Mozilla or in Firefox, it is that secret link. It's a link that gets created by the object function when it makes a new object which has a reference to an old object. So one way that we can use that is we can make the original object, the ancestor object, the old object. We could make it in any of the ways that we can make objects. And in JavaScript, the most convenient is often to make an object literal. So in this case, it has a first method and a second method. Then I can make a new instance of that object from the previous one. So now I have a new object. And I can go and augment it. I can add a third method to it. And then I can use it, that new object, as the ancestor of yet another one. And that one inherits the old method going back 2 generations of objects. So this is a very simple pattern for reuse of objects. I can make new instances without needing any classes. I just make one object that's pretty much like what I want, and then I can make lots more and customize it. And the way it works is if we try to access a property of an object and that object lacks that property, then we follow that linkage to the object that it inherits from and see if it has it. And if it does, then it provides the access. If the access fails, then we can continue the search from this one. This one will have a link as well, and we'll follow it as many times as we need to. Ultimately, it stops at object.prototype. Object.prototype is always the end of this chain. Because of the way that inheritance works, changes to the old object can be reflected in the new object immediately. So it's possible to augment an ancestor, and all the children, even the children that were created before you did the augmentation, may get that new property. But changes to this object will never have an effect on this one. The linkage only works in one direction. So the old object can be the prototype for any number of instances. And then the new object can also be the prototype, and we can continue that as far as we can keep in our heads. You can get to the point where it becomes unwieldy, but the JavaScript system does not impose any limits on how long this chain can get. Using the object function, we can quickly produce new objects that have the same state and behavior as existing objects. We can then augment each of the instances by assigning new methods and members. Now, Netscape, when they created JavaScript, didn't think of that. Even though they were modeling a prototypal language, it was maybe a little bit too radical for them. So they chose instead to have a notation which looked more like a classical notation. They tried to do both things at once, and as a result, didn't do either very well. I call the form that Netscape proposed pseudoclassical, because it's trying to look classical, but very quickly you discover that it isn't. And so the approach was to introduce operators, particularly a new operator, which followed some of the classical form. To do this, they provided three mechanisms. First was constructor functions, the next was the new operator, and then the next was the prototype member of functions. And by combining these three things, they get pseudoclassical inheritance. This is the basic pattern that you get in pseudoclassical. So first we start with a function, which will be the constructor. We can give it any name we want, but generally we give it an uppercase letter to identify it as a constructor. And in a little while we'll see why that's important. It will, what it's called with a new prefix, be given a new object which it can then customize. And it has access to that object through this. And after it's finished doing its customization, it returns this, although that return statement is optional. If a constructor returns nothing, instead of returning undefined, it will return the object being constructed. Then we do something, which looks really odd to people coming from the classical school, which means it looks pretty odd to everybody. We augment the constructor's prototype by assigning methods to it. And the idea is that each instance will inherit these methods. And because they're all shared through a prototype object, we don't have to consume memory for these methods for every instance. So there's some efficiency that comes from that. But it looks really odd because it's sitting outside of this, and the prototype notation is really unfamiliar. So but ultimately we use the new operator, and this looks kind of like Java. And that was sort of the point of this pattern, was to try to make the Java programmers familiar or comfortable with this pattern. But this stuff didn't fly. And so the Java community looked at this and freaked out and said, I don't know what this is, but this is not something we want to be associated with. But this is the way that Netscape proposed that we do programming. When functions are designed to be used with the new prefix, we call them constructors. Constructors are used to make objects of a type or class, or basically a pseudo-class, since ultimately the language doesn't have classes in it. And the notation looks a little strange because it's trying to look old and familiar, but it's really different. So the way that the new operator works is it returns an object with a link to constructor.prototype. So if we start with constructor.prototype and we make a new instance of a constructor, we get a new object with this link. The constructor function is passed the new object, and it's this variable. And this allows a constructor to customize the object before it returns it. One thing that's really dangerous about this pattern is that if you write a constructor which has to have a new prefix, but the programmer forgets to include the new prefix, bad things happen. It gets called as a function rather than as a constructor. And so this, instead of pointing at the new object to be customized, is pointing at the global object, because that's what happens in the invocation pattern. And then it will return the global object as though it was the instance it had just created. So you get two opportunities to be clobbering global variables. This is really bad. There's nothing in the language which gives you any indication that you made this error. There's no compile time check. There's no runtime check. The only clue that you get is that your program has crashed and things are acting really strangely. So that's the reason why we want to capitalize constructor functions, so that we've got at least one visual clue working for us that if I see a function that's got an uppercase letter, I can develop a reflex that tells me to always put a new in front of it. I consider this one of the serious design errors in JavaScript, but it's something we have to live with if we're going to use the pseudoclassical pattern. So whenever a new function object is created, it is always given a new prototype member, even if it's not intended to be used as a constructor, because the language itself has no way of knowing how functions are going to get used. And prototype object will contain a constructor member which points back to the original constructor function. That sounds a little odd. I'll show you a map in a moment which will make sense out of that. You can add other members to the function's prototype. These members are linked into objects that are produced by calling the function with the new operator. This allows for adding constants and methods to every object produced without the objects having to be enlarged to contain them, because they inherit those from the prototype. Some people call this differential inheritance, in which we only specify the differences from one generation to the next. So here's a bit of syntactic sugar, or maybe syntactic rat poison, which could be used to make this pattern a little bit nicer. I can write all functions inherit from the function object, and it has a prototype, and it can extend that, so that allows any function to have methods, which sounds a little odd, but that's the case. And then I can call it. So in this case, I define a method to which I can pass a name and a function, and that will bind it to that guy's prototype. Makes it look a little bit more classical, but it does exactly the same thing as what we were seeing earlier. JavaScript, because of its dynamic nature, allows us to write functions which act sort of like macros and give us a little bit more control over the presentation of the language. Is this a good form or a bad form? I don't have an opinion on that. It really depends on what style of programming you want to be pursuing. Okay, so that's basically how classes work in the pseudoclassical school. So how does inheritance work? This is where it gets really odd. We do inheritance by replacing the prototype of one constructor with an instance from another constructor. So if I want bigger constructor to inherit from my constructor, I replace its prototype object with a new instance. This is a really, really bizarre looking notation. This is even stranger than the .prototype stuff that we saw before. So let me give you an example to show how this actually works. We're going to start with a real simple pseudo class. We've got a gizmo, and the constructor will just make a new object, give it an ID property, and return it. That's pretty simple. And we'll also add to all of the instances a toString method, which returns the string gizmo concatenated with that same ID. So that's pretty simple. So this is a diagram of what's actually going on. The boxes represent the objects that are being constructed throughout this. This one is built into the system. This is the object, and object.prototype is this, which has a constructor field and the basic toString method, which is the end of everything. Then we've got our gizmo. That's a gizmo function of the gizmo constructor. It has a prototype member, which is this object, which contains a constructor and the new toString method that we defined up there and assigned it to the prototype. And then this is the new instance that we're making. Now, these constructor fields point back to the function that they are the prototype of. So we get a circular thing going on there, and object.prototype.constructor points back to object as well. This was intended as a way of identifying objects. You could ask an object, who's your constructor? And you might have a sense of what type it is. But as we'll see in a few minutes, it doesn't actually work. Okay, then we've got the true proto-links, which are the thing that allow the objects to inherit. The new gizmo that we make will inherit from gizmo.prototype, and that's how it gets its properties. And gizmo.prototype inherits from object.prototype. So any methods which we ask for, which aren't in that object, we'll try to get from here, and if they're not there, we'll try to find them there. Okay, everybody? So that's a simple gizmo. Okay, but now we want to do inheritance with that. And that means that we blow away a constructor's original prototype and replace it with an instance of another one. So here's another example. We've got a whosit. And our whosit has a similar constructor to the gizmo. We're setting an ID. And then for the who's it prototype, we replace it with a new instance of a gizmo. And we're going to extend the prototype by augmenting it with another method, this time a test method, which will return true if the ID we pass in matches. Okay, so here's the map that's going on here. Again, we've got the original gizmo that we saw in the previous example. Then we've got the who's it. Originally, who's it.prototype pointed at this, but because of that assignment we did, it's now pointing at this new object, which is an instance of gizmo. So when we put in the inheritance linkage, we see that the new who's it that we made inherits from who's it.prototype, which inherits from gizmo.prototype. And I didn't show the link here, but that inherits from object.prototype. So if we go to the new instance and ask for its ID, we find that there. If we ask for its test method, we find it there. And if we ask for its toString method, we find it there. Now, if we ask it for its constructor field, well, its constructor field used to be here, but that's been garbage collected, so that's gone. So when we ask for this instance's constructor, we'll get this one. And he'll identify himself as a gizmo, which isn't technically wrong because it inherits from gizmo, but it might have been more useful if it told us that it's a who's it, but it isn't. So this was, I don't know if it's an error or an oversight, but it's a problem in the Netscape model for pseudoclassical inheritance. So I think that's way too complicated. I think there's too much indirection in it. I think it's just not a good pattern. I much prefer using the object function to make instances of objects. It's more in keeping with the true prototypal nature of the language. But JavaScript doesn't have an object function, so we have to write our own. This is one of the primitive operations you'd expect to see in a prototypal inheritance language. They left it out. But fortunately, we can synthesize it. So in the pseudoclassical model, they had constructor functions, prototypes, and the new operator. We can use those to make the prototype operator. So this is why that works. We call the object function here to make a new object from an old object. First, it creates a function f, which has a prototype to an object, which has a constructor field, which points back to it. Okay, then we replace its prototype with the object that we want to inherit from. So its prototype pointer is now pointing at the old object. Then we make a new instance. Okay, so that will make a new object whose link points to f.prototype. So that gets us that. And then we garbage collect it, and we're left with that. So it's a little more than we want to do, but it's enough. I mean, working in the web, you spend a lot of time doing workarounds, and this is basically a workaround, but it works. And the reason it works is because of public methods. A public method is a function which uses this. So it assumes that it's getting called with the method pattern, which will bind it to this and allow it to operate on a particular object. In JavaScript, the binding of this in method invocations happens at invocation time. In most other languages, it'll happen at some earlier time, at compilation time, or perhaps at instantiation time. JavaScript does it very, very late, and that late binding allows for these functions to get reused dynamically. So you can take any public function or public method and stick it in any other object, and it'll probably work there. So that's a very convenient form of reuse. So the way you can identify a public method is it's got this in it somehow, and that access to this allows it to bind to any object. And we can put it anywhere and it works. Public methods work extremely well with prototypal inheritance and with pseudoclassical inheritance. We put them anywhere in the inheritance chain, and they'll work in all of the children. Now, if you're making a singleton, that is just one instance of an object, in most classical languages, you have to go ahead and make a class to define that one instance. In JavaScript, we don't have to do that. We can just make the one object and be done. That's a lot faster and a lot smaller. There's a lot less code to write. So one way to write a singleton, as we saw earlier, is I can just make an object literal, and I can put 2 functions in it, done. I don't need a class. I've got my object right there. But sometimes it'd be nice to have for those functions to share access to private variables and private methods. And generally, it's believed that JavaScript doesn't provide for private variables and private methods. But in fact, it does. And we'll look at some patterns that will allow us to achieve that. The key to it is the function nature of JavaScript. In some languages, you've got different syntax for functions, methods, constructors, classes, and modules. In JavaScript, functions do all of those things. So there's a much smaller set of mechanisms, but that mechanism is really powerful and does a whole lot of stuff. So if you think about modules, you want modules to contain your namespace so that references don't get leaked out and cluttered. So you want to be able to define variables in a module which are visible only inside of that module. JavaScript doesn't have modules, but it has functions. And functions have scope, so that variables defined inside of a function are not normally visible outside of the function. So using that, we can use functions to create module containers. And we want to do that because, as you recall from last time, global variables are evil. And JavaScript is particularly evil because of its dependence on a global namespace for binding everything together. So we need to be really, really careful as our programs get bigger and as we get more promiscuous in our mashups. We've got to keep them from stomping on each other. So we need to minimize global names. Module patterns allow us to do that. So here's another way of writing a singleton. We've got the same 2 methods that we had before, but this time those methods have access to private variables and private functions. And we define those up here inside of this function, which we then return a value to the singleton. And the thing which is maybe a little surprising about this expression is that we're assigning not a function to the singleton, but the result of invoking the function. Okay. And because of the principle of closure, these functions will continue to have access to this private stuff, to basically the members of their parent function, which is this one, after the parent function has returned, after the invocation is finished. So as long as these functions survive, which they will, stored as an object in the singleton variable, their binding to these variables will survive. Anybody have a question about this? This is a really basic pattern. It's important that everybody understand it.
So the reason that's a singleton is because you kind of instantiated it in line. Is that right?
That's right.
There's nothing that would prevent you from cloning the code and doing it again and call it secondton.
Absolutely, and we'll do that in a minute.
Okay.
One thing to recognize is that applications are singletons. Right? An application is one instance of an object which has the basic methods of an application. And we do that using exactly the same pattern. So I've got an application which I'm going to assign to a property in the Yahoo variable. Again, we want to do that so that we have no global variables or no additional global variables. Reduces the likelihood that we're going to have collisions. And this is our application. And we store it there, and it's just fine. Now these methods here do not use this to access the private stuff. They've got direct binding to that stuff. So it's a different kind of pattern. You could not pull these out and put them in another object and have them work the way they did before because they're not using this to provide the binding. So I call these privileged methods. These are methods, or these are functions that have access to secret information. They're not using this to access public information. They have access to private variables, private members, and privileged methods obtain their secret information through closure. Now, taking the idea that you proposed a minute ago, we can take that pattern and put it inside of a function and use that to make many instances. I'm calling that a power constructor. It's a constructor which knows how to make objects that contain privileged methods. So the way we do that is we take that singleton module pattern and we put it in a constructor. And it will basically work in 3 steps. All power constructors do this. We'll first make a new object somehow, and there are lots of ways to do that. We'll then augment it, and there are lots of ways to do that. We assign new properties to it, and then we return it. So 1, 2, 3, pretty simple steps. Here's a template for a power constructor. We can't be using this in a power constructor because we're not called that way. So instead we have that. So we avoid the reserved word problem. And we'll make an object because that's step 1. And I could use the object function to do that, or I could use the new method to do that, or I could use an object literal to do that, or I could call some other function that returns an object. That's enough. Anything that makes an object can be used in that first step. Then we'll define private variables and private functions. And then we will augment that with the new privileged methods that we want to assign to it. These privileged methods have access to that good private stuff, and then that gets returned. Okay, so we get lots of patterns available in the power constructor. We've got access to public methods, which we can inherit from the object that we start with. We've got private variables and private methods, and then we've got the privileged methods that we bind to that. So we've got lots more reuse patterns than we had before. And we don't need to use new anymore, as you pointed out. So we can just call the constructor as is. We can put new in front of it. Doesn't hurt anything.
So do you use new?
No, not anymore. In my own programs, the only place I ever use new is in the object function. That allowed me to factor it out of the language completely. So how can a power constructor inherit from another power constructor? Well, it turns out it works really, really well. It uses a model that I call parasitic inheritance. And I got the term from observing insects who create new offspring by laying their eggs inside the living bodies of other animals. So basically what they do is provide a little bit of customization information and let the other critter do all the work of making the new instances. And that's how this pattern works. And I'll show you an example. This is a little bit of code from a compiler that I wrote in JavaScript, which compiles JavaScript. And one of the things that you do in a compiler is create classes of symbols. Manipulating symbols is a lot of what a compiler does. So this is the constructor for a basic symbol. Basically returns an object literal. And then I've got a delimiter, and I want to make a delimiter, and what it does is call the symbol constructor and return it as though it had done it. Then I want to make a statement label, and I'll pass in the name of a statement like for, and a function which parses the statement, and it calls delimiter, and then adds some additional information. Then I got a block statement thing, which calls statement and adds an extra thing, and so on. So each of these does just a little bit of work, relying on someone else to do most of the heavy lifting for it. It just provides a little bit of customization. Let me show you another example. This is the Gizmo and Who's It demo that we saw a little earlier. Seeing them together, we notice a couple of things. One is that the Who's It wants to inherit from the Gizmo, and it has to repeat all the stuff in the constructor. And that seems really wasteful. You would think that code reuse would mean that you wouldn't have to duplicate the code.
Error prone too.
It is error prone. And then this notation still looks really odd, having the guts of the construction hanging out on the outside. So this is how we would write this in a more parasitic model. We'll start off with the Gizmo. We'll just return an object literal in this case, make it really, really simple. Then the Who's It will call Gizmo and make an instance. and assign it to that, and then we'll augment that and return it. Okay, so this is 1, 2, 3, real simple parasitic pattern. I think this reads a whole lot better than the pseudoclassical pattern. For one thing, it's all self-contained. It's all in there. Everything I need to know to make a who's it is right there. We got rid of the duplication of the setting of the ID property. We now let the other constructor do that for us. So that little bit of work went away. Just a little bit simpler. As we'll see, this is actually conforming more to what we do in a true classical pattern. It's just that it's happening dynamically at runtime rather than statically at compile time or class definition time. Now, I was telling you that one of the benefits of the parasitic inheritance pattern is that we can have private variables and private methods. In this case, I don't have any privacy going on. The ID is a public variable in the object. So I want to make good on the promise that we can make it private. So we'll, yeah.
Question. So let's say you make a two who's it object. Then each who's it object actually creates one gizmo object. So in the end, you have a two gizmo object, two who's it object.
No, because what it does is it makes a gizmo object and then transforms it into a who's it. So we're conserving the objects. At the end of the string of parasitic construction, we only make one object.
And you can continue that way.
It gets passed through several constructors along the way.
Oh.
Okay, so let's change this, making ID a private variable. And it turns out we actually save code by doing that. What we'll do is get rid of the this dot so that now ID is bound to the incoming variable. And closure keeps that connection, so it just works. And similarly, here the who's it has the same ID as we're passing to the gizmo, and we can do the same trick here. So all of these will just work. So we now have a shared private variable going through this chain of parasitic construction. Because of the closure property, inner functions, which is what this is, have access to the state of the outer function, even after the outer function has returned. So after the constructor has returned, this is still bound to that ID. Now, just to get, you can go really, really far. If you go out on the net, you can see people have come up with amazing patterns for how you can use these sorts of structures to do all sorts of stuff. Here's another one where we want to simulate sort of a package scope, where we want to have shared private information which is shared by these constructors. So the way we can do that is starting with the who's it now. We'll create an object which has secret stuff in it. And it could initially be empty, as it is in this case, but we could start by seeding it with some methods. And then we pass it along to the gizmo constructor. So it's a way of this constructor granting access to private information to that constructor. And what it does is it's got this extra parameter, and if we didn't send it one, then it'll make its own. And it could then augment it. It could add new methods to the secret, so we can get new package scope kind of stuff going on there. And then we can access it. In this case, we're just accessing a member through the secret, but we could have all sorts of methods and other really interesting stuff going on. And the who's it, if it had a statement here like that one, could have the same thing happen, so that someone could be passing secret objects into the who's it. In this case, it's final in that it's not going to let anybody pass a new secret object in. Okay, so I'm not going to claim that this is a particularly useful pattern, but for people who are coming from a Java environment where they depend on things like package scope and to share over multiple classes, this is a way of achieving a similar effect. It does basically the same things, except it's doing it at runtime. Some people like to have access to super methods. In my own work, I've found that I don't use them very much, but some people are comfortable with that pattern. So we can get access now to super methods. This is something we couldn't do with the pseudoclassical pattern, but we can do it here. When I access the gizmo, I can extract from it its toString method and save it for future use. Then I can access it here and invoke it using the apply method. I can cause it to get invoked because we keep this binding through closure. So I always have access to this super method independent of what I might have added to the object. So these are just a few of the inheritance patterns that are available to us in JavaScript. We've got prototypal inheritance, which works really well with public methods. We've got parasitic inheritance, which works really well with privileged methods and with public methods and private methods. And then we got pseudoclassical inheritance for the elderly. And we can take all of these and mix them together. So it's an amazingly expressive language. We've got many more patterns of code reuse than we have with virtually any other language. And we've got support for more sorts of programming styles than in any other language. We're seeing cases now where people are coming to JavaScript from Ruby, and they're bringing Ruby traditions with them, or they're coming from Python and they're bringing Python traditions to them. They're adapting the language to work in idioms which are familiar to them. I don't necessarily recommend that because I'm more about trying to discover how to do this language efficiently. And if you bring baggage from other languages, then it's easy to miss that stuff. But the language is remarkably expressive and tolerates this kind of experimentation better than any other mainstream language. So I like working with the grain, trying to discover what is the language really good at, what does it really want to be doing, and then exploring programming patterns which best exploit that. I find that the pseudoclassical pattern that was intended to be built into the language is really less effective than the prototypal patterns or the parasitic patterns. They all start with P. I don't know why that occurred, but they do. We do not need formal classes for reuse or extension. One bit of advice, though, is that I think it's good to be shallow. People coming from some classical languages get into really, really deep hierarchies. And because stuff gets bound statically, there's generally not a lot of overhead in that. In this language, we're doing similar structures except they're dynamic. And so we actually do pay a cost for deep hierarchies. So generally, it's much better to go shallow. But very often, we don't need to do much inheritance at all because we can customize and make new objects at will. The way you think about classes don't necessarily apply to this language. Let me give you another coding example. It shows another use of closure. When we're doing AJAX applications, very often we'll have something in the UI which we'll want to do something in a little while or go away in a little while. We want to do timing-based stuff. JavaScript provides, or the browser provides, a set timeout function, but it's not very object-oriented. And so we'd like to be able to talk about time using the same object notation that we do everything else. So I propose a later method, which we can call on any object, and we'll pass it some amount of time, and say, in 100 milliseconds, let's call myObject.erase and pass it true as its parameter. So you can imagine a lot of UI situations where something like that would be very useful. And this is how we would code it in JavaScript. We can augment object.prototype so that all objects in the system will inherit the later property. So that becomes really powerful. All objects now will understand later. And we'll pass in milliseconds in a method. We'll deal with the arguments in a moment. We're doing this little trick here where we assign this to that. And the reason for that, reason for this, I guess it is the reason for that, is because when the inner functions do not have access to the this of the caller. I think that was a design error, but it's something we have to live with. So to get around that design error, I make a variable with the same value, and that variable does get delivered to the child. Then I have to get around another design error. in JavaScript 1.0, there were no arrays, but people started acting as though it had arrays anyway. Since it had objects, and all subscripts got turned into strings, you could treat an object as though it were an array. The only limitation was it didn't have useful methods on it, and it didn't have any sense of its own length, so they were a little awkward to use. So in JavaScript 1.1, they made array a real type. But basically, it's still an object. Array in JavaScript inherits from object. It just has more methods, and it has this tricky length field. Now, in the original JavaScript, the arguments array wasn't an array, it was an object, because they didn't have arrays in JavaScript. And when they added arrays to the language, they forgot to fix that. So arguments continues to be an array-like object. It has a length property, but it doesn't have array nature. In particular, it doesn't have the array methods, which is a shame because I want to treat it like an array. I want to take the arguments array, chop off the first two items, and take the rest of it and use it because I need that. But what I can do is I can go to array.prototype because it contains all of the methods that arrays have. And I can get the method that I want, in this case the slice method, and then I can use the apply method on it to invoke it. And I will invoke it by binding this to the arguments array and then passing it the number 2, which is the parameter or the index at which I want it to start slicing. Shouldn't be necessary to do that, but it is. And again, it's because Microsoft copied that first error into JScript. And when they went to ECMA to create the standard, Microsoft insisted that they keep it that way. I think we're finally going to get that fixed in the 4th edition of JavaScript, but I'm not confident. There's going to have to be a survey to see how many programs break because arguments becomes a real array. Anyway, so we have accomplished that, so we now have an array containing that true thing. If you remember from this, this is parameter or index 2. So everything from here on, everything from here on gets put into the arguments array. Then a little bit of user convenience. If the method parameter that we got passed in was a string, then we'll look it up for them and find it in the object and save it there. Otherwise, we assume that it's a function. And then we call set timeout, and we set pass to set timeout a function which will call that method, binding it to that and passing it the array of arguments. And it will get invoked in that number of milliseconds. So that's how we could do a later function. And the really nice thing is that we can do this trick with augmenting objects all over the system. But there is one caveat. There's a problem with the for in statement. When it does its iteration, it will dredge this up along with all the other values that you want. And so in the first class I showed you that when you write a for in, it's a really good idea to put an if statement as the first thing in the for body to filter out stuff like this that you don't want it to dredge up. Suppose we've got a loop in which we've got a number of objects that we're going to be assigning functions to. For example, assigning event handlers to divs in a browser application. If we're not aware of how closure works, we can cause strange bindings to happen on those functions, and they won't resolve the way that we would like. This was an example that was on Develop Front End last year. Someone was going through a list of divs, and for each one, he was assigning a mouse over function. And each of the mouse over functions had a div ID. But he found that when he ran it, every object thought it had the same ID. And they all had the last ID. And he couldn't figure out what was happening. And the reason was because of closure, you get bound not to the value of that at the time you call it, you get bound to its current value, which can change over time. So the solution, as most problems in JavaScript requires putting another function in there, and then everything works okay. So what we did was, instead of assigning this function to the handler, we assign the result of calling a function to the handler, which returns that function. Okay, and it's a weird little bit of indirection, but it causes everything to work out right. So we pass in the div ID that we want here, which gets bound to this ID here, which gets bound closure to that. So that allows each one to keep its own ID, and it doesn't get confused. Now, as our programs get larger and more complex, debugging becomes really, really important. And for a long time, it was possible to debug JavaScript without debuggers, using alert methods and dumping stuff to a div and so on. And those can still be useful. But our programs have gotten so complex now that you absolutely have to have a debugging tool. Otherwise, there's no way to manage the complexity. Fortunately, there are a number of tools available to us. On IE, we've got the Microsoft Script Debugger, which is available in at least 3 forms. There's a free download version, which I don't recommend. It's just not good. I'm sorry, did someone say crap?
Yeah.
yeah, it is crap. Then there are 2 versions which are very good. One of them is built into Office, and the other is built into Visual Studio. You can get a copy of Visual Studio Express, which is free, which has the good debugger in it. Or you can go get the other free debugger, which is bad. I've asked Microsoft, why do you do that? Because they get a lot of reputation hit. There are people who download the free one, and they go, well, this is awful. Microsoft doesn't have a good debugger. In fact, they do. I think the best web debugger right now is Microsoft's, although that may change soon. In the Mozilla world, there are 2 debuggers right now. There's Venkman, which is strongest in Mozilla. It's usually broken in Firefox. It's not being kept up to date very well. Then there's a new debugger coming up called Firebug, which is on Firefox, which is very good, but it's not complete yet. But if it continues to mature at its current rate, I expect it's going to probably be the best of breed debugger soon. But it's not quite there yet. So for now, Venkman is probably a better choice. Then in Safari, they're developing a new debugger called Drosera, which is not fully cooked yet. So it's not yet a viable option, but I expect it should be sometime later this year. So to get the Microsoft debugger, I'm assuming that you've got Office on your machine, since everybody's got a copy of Office. So if you do, you can go to the Office setup, and buried under Office Tools, under HTML source editing, under web scripting, there is an option for web debugging. You've got to get all the way in there and turn that on. It's really deeply hidden. If you don't know where it's hidden, it's very difficult to find. And so most people have it turned off. But I recommend turning it on. Now, once you do that, you're still not done. You then have to go to the Internet options, go to the Advanced tab, and go to the Browsing section, and don't get confused by the double negative here, disable script debugging. You want to uncheck those so that debugging will be enabled.
Designed by the
Okay, once you've done all of that, you can now do debugging in IE. And the way you get access to the debugger is you go to the View menu. You now have access to Script Debugger. And generally, you'll want to open it. And when you open it, you'll get something like this. There are lots of panels and windows in here, and you've got a lot of control over how you can set them up and customize them and stuff. So it won't look exactly like this, but all the pieces will be here, and you can arrange them. I found this setup is effective for me. You may want to do similar things. So here's what you get. You get a source window, which shows you the source of the thing that you're currently looking at. There's a place in the margin where you can set breakpoints. So when the JavaScript interpreter hits that point, it'll stop and open the debugger, and you can look at what's going on. That's really nice. It shows the line that you're currently executing in yellow. You have access to the local variables, so everything which is local to the current function is visible here, except for this. The guy who wrote this for Microsoft didn't know how this worked, and so
Make this work.
so this isn't there. However, you also have a watch window where you can type in any expression, and the value will be shown in the next column. And you can put this in there.
Watch this.
Yeah, you can watch this. And one nice thing about the watch window is that it can open up an object. So it'll show you the object tree, so you can see everything there. You can inspect the state of the object. You can modify its contents, so that's really useful. You have access to the call stack, so you can see where you currently are, and you can click on any of the places in the stack and then see the code that you're in at that level on the stack. That's really useful. And when you do that, the local variables will reflect the level of the call stack that you're currently looking at. That's very nice too. And there's a window which shows all the script files and HTML files which are currently open. So if you need to set a breakpoint at something which isn't currently in this window, you can click on it there and bring it up and put the breakpoint in it. And then there's an immediate window down here where you can type in any JavaScript expression and it'll get executed. So that's a handy thing for testing. So that's basically the IE debugger. As you would expect, it has some bugs in it. One of the most annoying ones is that you cannot set a breakpoint on the first line of a function, which is really irritating because usually that's the place in the function you most want to set a breakpoint. So to get around that, I have sometimes created a new var, var x equals 0. I don't use an x, I just need it there so that I've got a sacrificial first line that I can go past so that I can set the breakpoint to where I really want to break. I'll show you another alternative in a moment. Then there's Venkman. Venkman works pretty well in Mozilla, doesn't work very well in Firefox. Fortunately, Mozilla and Firefox can cohabitate. So you can keep both installed and use one for some stuff and one for the other. And their models are similar enough that if it works in one, it probably works in the other. So I keep Mozilla around just for debugging. So if I want something to debug, I'll open Mozilla. Generally in Mozilla, it comes already installed. When you're installing it, just make sure that the debugger box is checked on the setup, and then you're done. That's all you need to do. Once you've got it, to turn it on, you go to the Tools menu, go to Web Development, and then turn on the JavaScript debugger. And there's some developer toolbars which will provide a button that makes that a little bit easier to do. When you open it up, you get a similar display, basically the same set of components, a little bit more awkward in the way they're put together. You've got a text window here, again, with a place where you can set breakpoints. There's a tab here which shows you the scripts that you've got currently loaded, and you can click on them to get them to view here. You've got a list of local variables in this tab, and you've got the watches in this tab. Unfortunately, you can't see the local variables and the watches at the same time. It's really annoying. And the interface for setting watches is much more difficult to use. You can't just click on where you want the watch to be and type. You have to alt-click and select a thing that says, I want to make a new watch. One thing they did do that was right, though, is that this is included with the local variables. So you can get at that pretty easily. What else we got? We got the call stack, and we've also got a list of breakpoints. So you can see what breakpoints you've got set. Then there's a results window here, and you can type expressions in here and have them evaluated. So for the most part, it's very similar to the debugger that you get in IE. They're slightly different in the way that they get started and the things you have to do before you can work with them. Generally, you'll load a page, then pop the debugger open and set the breakpoints. But sometimes you've got something where you need to start debugging before you get control back. Like you've got a load time error, and there's not time to open the debugger and set a breakpoint before things have gone horribly wrong. So you'd like a way to automatically or programmatically create breakpoints. And fortunately, there is a way to do that. The JavaScript language does not include a debugger statement. If you look at the ECMAScript standard, debugger is a reserved word, but there's no description of a statement that corresponds to that word. But all implementations of JavaScript have a debugger statement. And what it does is cause a breakpoint if there's a debugger present. And the nice thing about it being a statement is you can execute it conditionally. So you can wrap it around, or wrap an if statement around it. You know, if we're in a situation where some variable is out of whack, or the control key is held down, or some other things going on, only then do debugger, and that will cause a break to occur. Yeah.
Does the language include an assert?
The language does not include assert.
So you could make this some form of reasonable assert for reuse?
Yeah, and some people will write assert macros or pseudo macros that do something like that. So you can have an assert function which will call or execute debugger. So it's often very important to consider performance in our applications. We want to provide a good experience to our users. We want to be respectful of their time, not keep them waiting, not frustrate them. But we also need to remember Hoare's dictum: premature optimization is the root of all evil. And if we optimize prematurely, we increase the brittleness of the code and often will compromise our efforts for long-term efficiency. So the first priority has to be correctness. Doesn't matter how fast it goes if it isn't right. And then optimize only when necessary. I often see that people, if their stuff is going too slow, don't consider algorithmic improvement. So it might be that they've got an n-squared algorithm going on, and they're trying to recode that and make it go as fast as possible. But it could be that there's an n algorithm available to them that doesn't matter how effectively it's written, it's going to run a lot faster. We also need to be watching out for limits. As we push the size of the working sets in the browsers, they get slower. And we need to be aware of the effects of memory consumption on the performance of the browsers. There are two places, though, where I recommend writing optimally all the time. Because JavaScript was intended as a simple scripting language, it doesn't attempt to do any kind of optimization of its code. The assumption is that it would take more time to optimize the code than you would save in its execution. That was true back when you were doing rollovers and form validation. But today we got these really heavy AJAX applications, which are really full-fledged applications. And we're suffering from not having that basic level of optimization. So two things which are very commonly done in most other languages, common sub-expression removal and loop invariant removal, are easy to do yourself. And I recommend in most cases you go ahead and do it. So here's an example of a sort of ordinary piece of code that you see in a lot of web applications. We've got a loop where we're going through a set of divs, and for each div, we'll set the color and the border and the background. But you can see there's some inefficiencies here. One of a really small one. This one's probably not worth worrying about. There's actually a little bit of computation in here where we resolve the div and get its length. Probably not significant, but we could factor that out. A much bigger win is we're looking at div sub I 3 times each time through this loop. We only really need to go through it once, so we could factor that out. Also, we're computing this thickness every time through the loop, but it never changes in the loop. So we're doing this concatenation n times. No reason to do it more than once. So we could refactor it. We can create some new variables. Variables are really cheap in JavaScript. So we can compute that once. We could cache the length as well, as long as we're going to the trouble. And then within the loop, we'll cache that value, and then we're done. I think this may have had the effect of making the code a little bit smaller. I think it might also be a little bit easier to read. One way you see people make decisions about how they're going to implement stuff is, I could do it using technique A or technique B. I'll do them both 10,000 times and look to see which one's marginally faster, and that's the one I'll pick. And often that will lead you to make bad decisions about efficiency. For For example, in JavaScript, we can do concatenation using the plus sign. And in JavaScript, string concatenation is just as ineffective as in Java. It's really not very clever at how it does that. So if you do lots of concatenations, you're going through a lot of intermediate results and churning up a lot of memory. So an alternative to that is to use the array join method, which goes through each element of an array, turns that element into a string, and concatenates them together. For large sets of stuff, that can be significantly faster than doing plus, 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 plus. So hearing that array join is faster, I've seen people create an array of two things and then join it, which is strictly slower than doing that. They drew the long lesson from this construct. Generally, if you're concatenating a small set of things, performance is not an issue. And if it's a really small set of things, it's going to be faster to do the simple concatenation. Only if you're doing something really big and heavy, like you're building a big HTML text that you're going to do an inner HTML on or something of that sort. In that case, you want to consider using join because the performance difference will be significant. But you don't want to be doing that for trivial operations. One of the ways that we can make programs faster is to improve their loading times. And it turns out that page loading is really sensitive to the size of the JavaScript files. So if you can make the JavaScript files smaller, they will load more quickly. One way that we can do that is to remove the unnecessary white space and comments from the file, essentially compiling the JavaScript. That's as close in a load and go language as we get to. Yeah, it is pre-processing. So minification does that. There's another technique which is related to minification called obfuscation, which attempts to go further. It will look at long names and try to change them into short names. The problem with that is in a language as dynamic as JavaScript, that can introduce errors. I mean, the scope rules in JavaScript can be a little difficult to understand, as we've seen, and there's an equivalence between dot notation and substring notation or subscript notation. So sometimes names and strings have a correspondence. Obfuscators, especially aggressive ones, have been known to inject errors into working programs, and because all the names were changed, they become virtually impossible to debug as well because you can't figure out what's going on. I think programming is already hard enough. I just don't have time for tools that could inject errors into working programs. So I recommend just doing the minification. I think that's enough, particularly if you then take the step of gzipping. Minification followed by gzipping, very, very effective. We should be doing that on everything. We should never be sending JavaScript that has not been gzipped. Let's see, finally, we're going to talk a little bit about JSON, JavaScript object notation. JSON is a subset of JavaScript which is now being used for language-independent data interchange. It's text-based, lightweight, easy to parse, and is strictly a subset of ECMA 262, which is the JavaScript edition, or third edition standard. We express the syntax or the grammar of JSON in these railroad diagrams, which show its simplicity, and I think they're pretty easy to understand. So an object is a thing wrapped in curly braces with keys or names as strings separated by colons from values, which can be any JavaScript value with commas separating those. So basically these are JavaScript object literals. That turns out to be a really convenient notation for doing data interchange. Unlike XML, we don't have to convert our programming language structures into document structures and then back again. We can start with programming language structures in one language. This structs, records, objects, dictionaries, hashes, all of those things map directly onto the structure. And so we don't have to have heroic transformations in order to get the data across. This is the structure for arrays, even simpler, just a set of values in square brackets. These are the values in JSON: strings, members, objects, arrays, true, false, and null. We don't have undefined because we're trying to be language independent. We don't have nan, again, because we're trying to be independent of any numerical representation. So we can go between lots of different languages. This is the syntax for strings. Basically, all C family languages use these conventions for strings, so it's very compatible. So if you've got two C-like languages, like JavaScript and PHP, for example, and they want to communicate, it makes sense that they communicate using their strings using a mechanism that looks like the way they think about strings. And this one looks a little bit like a trumpet. So the music goes in there and goes round and comes out here. It's a little simpler than the numbers in most languages in that we're not supporting octal or hex, and that's because of our goal to be minimal. For data interchange, we generally don't need those formats. But it provides for integers, real, and scientific. And another aspect of JSON is that in JavaScript implementations, we're sending JavaScript basically to another site and evaluating it, which is potentially unsafe. So to make JSON safe, it has a regular expression which looks for anything which is not strictly JSON before it does the eval. So that way we can be sure there are no functions or invocations or anything which could cause badness to occur. And having a simple string format makes that validation a lot easier to do.
So is eval automatically checks the data?
No, eval doesn't do that. Eval just looks to see if it's valid JavaScript, which means it's not safe. But we're wrapping that now with a regular expression. So we do the eval only if the regular expression tells us it's not dangerous.